You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your educational journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. Observability in large language model applications refers to the ability to monitor, measure, and understand how systems behave across their entire lifecycle. It is not simply about collecting data, but about generating actionable insight from that data so developers, operators, and stakeholders can see what is happening under the hood. In traditional software, observability involves metrics, logs, and traces that reveal how requests move through systems. For AI, the challenge is greater because the outputs are not deterministic. A model may provide different responses to similar inputs, and failures are not always obvious. Observability fills this gap by creating transparency. It transforms the opaque, probabilistic behavior of language models into something that can be studied, audited, and improved. Without observability, teams are flying blind, reacting only after users complain or failures cause damage. With it, they gain the visibility needed to ensure performance, safety, and compliance in real time. The importance of observability in AI systems becomes clear when we consider their role in sensitive environments. A chatbot used for casual entertainment may survive occasional failures without much consequence, but a legal assistant, healthcare triage system, or financial advisory bot cannot afford even rare lapses. In these settings, errors can create regulatory violations, financial loss, or even risks to human well-being. Observability ensures that developers can detect errors early, measure quality consistently, and verify that outputs align with compliance standards. It provides the feedback loop necessary for continuous improvement. Beyond safety and compliance, observability supports operational excellence. It allows teams to understand where bottlenecks occur, how costs accumulate, and how user interactions unfold. In short, observability is not an optional feature of large-scale AI deployment, but a non-negotiable foundation for responsible, sustainable adoption. The key dimensions of observability in AI include traces, spans, and logs. These categories represent different levels of detail about what the system is doing. Traces capture the full journey of a request through the system. Spans break that journey into smaller steps, and logs record specific events, such as prompts and outputs. Together, they provide a multi-layered view of performance. Traces answer the question of what happened from start to finish. Spans show what happened at each stage along the way. Logs provide granular details about what was said or done at specific points. This layered approach is necessary because no single perspective is sufficient. Like medical imaging, where doctors rely on X-rays, MRIs, and blood tests together, observability in AI requires multiple forms of telemetry to reveal the full picture of how applications behave. Traces play a central role in understanding AI pipelines. They map the end-to-end flow of a request as it travels through different components, from initial input to final output. For example, a trace might begin when a user submits a question, continue through the retrieval of relevant documents, pass into the model's generation phase, and conclude when the response is returned. By visualizing this flow, operators can see how long each step took, where failures occurred, and how the request was shaped along the way. In complex pipelines that include retrieval-augmented generation or multi-agent orchestration, traces provide a roadmap of execution. They answer not only whether the system worked, but how it worked. Without traces, diagnosing failures is like trying to fix a car without ever opening the hood. With them, developers see the journey in detail and can identify precisely where interventions are needed. Within each trace, spans provide finer detail by breaking the process into discrete components. A span might represent a single database query, an embedding retrieval, or a call to the language model itself. Each span can be timed, monitored, and evaluated individually. This granularity helps identify bottlenecks or inefficiencies. For example, if a system consistently spends excessive time in one span, such as document retrieval, developers know where to optimize. Spans also allow for correlation. If one span fails, the trace shows how that failure propagated downstream. This helps teams distinguish between local issues and systemic ones. By analyzing spans, organizations can ensure that every stage of the pipeline is operating within expected parameters, contributing to the overall reliability of the application. In effect, spans are the microscope within the telescope of traces, zooming in to reveal the fine-grained workings of AI systems. Prompt logs are another indispensable tool for observability in LLM applications. They record exactly what input was sent to the model and what output it returned. This is essential for debugging, auditing, and improvement. Without prompt logs, developers cannot verify whether a failure arose from a flawed prompt, an unexpected model behavior, or a downstream processing error. Prompt logs also serve as evidence in compliance contexts, showing regulators what instructions were given and what responses were produced. They support reproducibility, allowing teams to rerun problematic prompts to test fixes. At the same time, prompt logging must be handled carefully to avoid privacy risks, since logs may include sensitive user data. When managed responsibly, prompt logs transform black box interactions into transparent exchanges that can be studied, refined, and improved systematically. Token usage monitoring provides another dimension of observability, focused on performance and cost. Since LLMs operate on tokens, each representing fragments of text, tracking token counts reveals how resources are consumed. Excessive token usage can drive up costs and slow performance, while insufficient tokens may truncate important context. Monitoring usage allows teams to balance efficiency with completeness. For example, a system that consistently uses far more tokens than expected may be inefficient in its summarization or retrieval strategies. Conversely, one that uses too few may be dropping vital information. Token tracking thus provides both economic and operational insight. It allows organizations to forecast expenses, optimize workflows, and ensure that models are neither underutilized nor overburdened. In large-scale deployments, where millions of tokens are processed daily, this level of visibility is essential for sustainability. Latency tracking complements token monitoring by measuring how long each stage of the pipeline takes. Users are sensitive to response times, and delays can erode trust or usability. Observability systems measure latency across spans, showing how much time is spent on retrieval, generation, post-processing, and delivery. This allows developers to pinpoint bottlenecks and optimize accordingly. Latency tracking also helps balance trade-offs. For example, deeper summarization may improve accuracy but add delay. By measuring latency, teams can decide whether the trade-off is acceptable for their use case. In mission-critical applications like fraud detection, where decisions must be made instantly, latency metrics are especially important. Observability ensures that response times remain aligned with user expectations and system requirements, turning performance into a measurable, optimizable parameter rather than a vague aspiration. Error tracking is another pillar of observability. Models occasionally fail, whether through timeouts, malformed outputs, or unexpected behavior. Observability systems record these failures systematically, noting what type of error occurred, where it occurred, and what impact it had on the overall workflow. Without this data, errors may appear as isolated incidents, leaving teams to guess at their root causes. With error tracking, patterns become visible. If timeouts cluster around certain spans, or malformed outputs arise from specific prompts, teams can target fixes efficiently. Error tracking also supports reliability by ensuring that failures are not silent. They are captured, logged, and acted upon, reducing downtime and improving user confidence. In essence, error tracking turns unpredictable failures into manageable events, ensuring that systems are resilient rather than fragile in the face of imperfection. Bias and safety monitoring extend observability beyond technical metrics into ethical territory. AI systems can produce outputs that, while technically valid, violate ethical guidelines or safety policies. Observability ensures these incidents are detected. Systems can log when outputs contain biased language, unsafe recommendations, or content that violates moderation policies. This provides visibility not only for fixing problems, but also for demonstrating accountability. Organizations can show regulators, auditors, and users that they are actively monitoring for safety issues. Bias and safety monitoring also create feedback loops for model improvement, helping developers refine prompts, adjust training data, or strengthen guardrails. By embedding ethical oversight into observability, organizations ensure that safety is not a static layer, but a continuously monitored aspect of system behavior. User behavior telemetry adds another dimension by capturing how people interact with the system. This includes what queries they submit, how often they engage, and how they respond to outputs. Telemetry provides context for evaluating system performance. For instance, if users frequently rephrase questions, it may indicate that responses are unclear. If they disengage after certain outputs, it may signal dissatisfaction. By analyzing interaction patterns, organizations gain insight into user experience, allowing them to improve not only technical performance but also usability. However, user telemetry must be balanced with privacy. Collecting too much detail without transparency can erode trust. When handled responsibly, telemetry provides valuable signals that help align system behavior with human expectations and needs. Compliance requirements make observability not just a best practice, but, in many industries, a legal necessity. Sectors like finance, healthcare, and government often mandate logging for accountability. Organizations must be able to demonstrate what inputs were processed, what outputs were produced, and how errors or interventions were handled. Observability provides the audit trails needed to satisfy these requirements. Without them, organizations risk fines, sanctions, or loss of trust. Compliance-driven observability ensures that systems are not only functional, but also accountable. It demonstrates that AI is operating within legal and ethical boundaries, which is crucial for adoption in sensitive domains. This accountability is what makes observability a pillar of enterprise readiness, rather than a technical afterthought. Data retention is one of the challenges of observability. Collecting logs, traces, and telemetry generates enormous volumes of information, some of which may contain sensitive user data. Retaining this data indefinitely raises privacy and security risks. Systems must therefore balance the need for transparency with the responsibility to protect users. This often involves retention policies that specify how long data is kept, how it is anonymized, and when it is deleted. Encryption and access controls further protect observability data from misuse. Without such safeguards, observability can become a liability. With them, it becomes a powerful tool for improvement and accountability that respects user rights. The challenge is finding the balance between sufficient monitoring and minimal retention, ensuring both visibility and privacy. At industrial scale, observability is indispensable. Enterprises deploying AI across thousands of users and millions of queries cannot rely on anecdotal feedback or spot checks. They need systematic, scalable observability frameworks that capture performance, cost, safety, and compliance data continuously. These frameworks allow organizations to operate AI as dependable infrastructure rather than as experimental tools. Industrial observability means not only detecting failures, but also predicting them, reducing downtime, and optimizing resource use. It ensures that AI systems remain aligned with business goals, regulatory requirements, and user expectations even as they scale. In this sense, observability is not just a technical feature, but a business enabler, making large-scale AI adoption possible by providing the trust and transparency needed for sustained investment. As AI expands into multimodal systems that integrate text, images, audio, and video, observability will grow even more important. Monitoring these systems requires tracking not only text prompts and outputs, but also image metadata, audio features, and cross-modal interactions. Observability thus becomes the foundation for advanced evaluation, ensuring coherence across modalities. By laying this foundation now in text-based systems, organizations prepare themselves for the broader challenges of multimodal monitoring. Observability ensures that as systems become more complex, they remain transparent, accountable, and reliable. This continuity leads naturally to the next discussion, where the focus expands from monitoring language models alone to evaluating and observing multimodal AI applications that operate across diverse data types and contexts. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Granularity in traces determines how detailed the view of a system's behavior can be. Fine-grained traces capture every small step in a workflow, such as the timing of database queries, the length of retrieval operations, or the structure of intermediate prompts. This level of detail is invaluable for debugging complex issues because it allows engineers to pinpoint precisely where things go wrong. However, fine-grained traces also generate vast amounts of data, which can be expensive to store and process. On the other end of the spectrum, coarse-grained traces summarize broader steps, such as input, model generation, and output. These are easier to manage but can obscure critical details. Organizations must therefore decide how much granularity is appropriate for their use case. High-stakes applications such as healthcare or finance often favor detailed tracing for accountability, while casual consumer applications may prefer efficiency. Balancing granularity ensures observability remains both effective and sustainable, tailored to the risks and goals of each system. Aggregation of metrics helps transform the raw flood of logs, traces, and spans into information that is digestible and actionable. Rather than asking developers to sift through thousands of individual events, observability systems consolidate data into dashboards and reports. For example, instead of showing every trace of a chatbot conversation, the system might summarize average response times, error rates, and token usage over the past week. Aggregation makes it easier for decision-makers to spot trends, such as a gradual increase in latency or a spike in errors tied to a recent model update. It also facilitates cross-team collaboration, since executives, compliance officers, and engineers can each view metrics relevant to their responsibilities. Aggregation transforms observability from a technical exercise into a tool for organizational learning, helping leaders make informed decisions about performance, safety, and cost. Alerting mechanisms provide the real-time responsiveness that observability systems need to be effective. When anomalies occur, whether a sudden surge in latency, an unexpected spike in token usage, or repeated violations of safety rules, alerts notify operators immediately. These alerts can take the form of emails, dashboard notifications, or even automated triggers that initiate corrective actions. The goal is to shorten the time between a problem emerging and a response being deployed. Effective alerting systems are finely tuned to avoid both false positives, which overwhelm staff with noise, and false negatives, which allow critical issues to go unnoticed. Striking this balance ensures that alerts inspire confidence rather than frustration. Well-designed alerting mechanisms make observability proactive rather than reactive, catching problems before they affect users, and giving organizations the agility to respond quickly to evolving conditions. Correlation with outcomes elevates observability from a technical tool to a strategic asset. Raw metrics such as latency or error rates are valuable, but their true importance lies in how they affect business or user outcomes. For example, a half-second increase in response time may seem minor from a technical standpoint, but could correlate with higher user abandonment rates in a customer service bot. Similarly, prompt errors might lead to compliance risks in regulated industries. By linking logs and traces to outcomes like customer satisfaction, retention, or regulatory performance, organizations can prioritize interventions that deliver the greatest impact. This correlation ensures that observability drives not only technical optimization but also business success. It turns monitoring into a feedback loop that connects the inner workings of AI systems with the goals and needs of the people who rely on them. Scalability is one of the greatest challenges of observability frameworks in large AI deployments. A single system may generate millions of logs, traces, and telemetry points daily, creating enormous volumes of data to store, process, and analyze. Without careful design, observability infrastructure can become a bottleneck, consuming resources faster than they deliver insight. To scale effectively, organizations use distributed storage systems, automated aggregation pipelines, and selective sampling strategies that capture representative data without overwhelming the system. Scalability also involves governance deciding what data must be kept for compliance, what can be summarized, and what should be discarded. Building scalable observability frameworks ensures that systems remain transparent even as they expand to enterprise or global scale. Without it, organizations risk drowning in data, with monitoring tools producing more noise than clarity. Scalability ensures observability remains practical, useful, and aligned with the growth of AI adoption. Integration with existing tools is another practical dimension of observability. AI applications do not exist in isolation. They operate alongside traditional software systems with their own monitoring infrastructures. Observability for AI must therefore connect seamlessly with established frameworks such as Prometheus, Grafana, or enterprise observability platforms. This integration ensures that AI telemetry is viewed in the same context as other operational data, enabling holistic management. For example, a sudden slowdown in an AI chatbot might be correlated with increased load on a database already tracked by existing systems. By unifying these views, organizations can diagnose issues faster and more accurately. Integration also reduces training overhead, since staff can work within familiar tools. This compatibility reflects a broader principle. AI systems should enhance, not disrupt, established practices, and observability frameworks must bridge, rather than fragment organizational monitoring efforts. Real-time versus batch monitoring represents another trade-off in observability design. Real-time monitoring delivers insights immediately, allowing organizations to respond instantly to anomalies or failures. This is crucial in contexts like fraud detection, where delays can mean financial loss. Batch monitoring, by contrast, processes data periodically, such as every hour or day, offering efficiency and reduced resource demands. It is suitable for contexts where immediate response is less critical, but long-term trends still matter, such as evaluating the effectiveness of summarization workflows. Many organizations adopt hybrid approaches, combining real-time alerts for critical events with batch analysis for broader insights. This balance ensures that observability provides both agility and depth, catching urgent issues while also supporting strategic evaluation. The choice between real-time and batch depends not only on technical capability, but also on business priorities and risk tolerance. Evaluating the success of observability systems involves measuring their impact on operations. Key metrics include mean time to detection, which tracks how quickly issues are identified, and mean time to recovery, which measures how quickly they are resolved. Reductions in these times demonstrate effective observability. Success is also reflected in reduced downtime, improved compliance rates, and higher user satisfaction. Observability is not valuable if it generates data that is ignored or misunderstood. Its value lies in improving outcomes. Evaluation ensures that observability frameworks remain focused on delivering practical benefits rather than becoming academic exercises. Organizations that regularly measure the effectiveness of their observability practices ensure continuous improvement, keeping systems aligned with both technical excellence and business needs. Security implications must also be considered. Observability data often includes sensitive information, such as user inputs, system prompts, and even intermediate outputs that may contain personal or confidential details. If these logs are not properly protected, they become targets for tampering or unauthorized access. Attackers could exploit logs to infer business operations, extract user data, or manipulate monitoring systems. To prevent this, observability frameworks must include strong encryption, access controls, and auditing mechanisms. Security ensures that the very tools designed to protect systems do not themselves become vulnerabilities. In high-stakes industries, regulators may require organizations to demonstrate that observability data is handled securely, adding another layer of accountability. By integrating security into observability design, organizations preserve trust and ensure that monitoring systems strengthen rather than weaken overall defenses. Cost trade-offs are inevitable in observability. Detailed logging, fine-grained tracing, and extensive monitoring consume storage, computation, and human attention. At scale, these costs can become significant, especially for enterprises processing millions of interactions daily. Organizations must decide how much detail is necessary to maintain safety and performance without overburdening infrastructure. Techniques like selective sampling, aggregation, and retention limits help manage costs by capturing essential data while discarding redundancy. Cost management ensures that observability remains sustainable, aligning the expense of monitoring with the value it provides. In many cases, the cost of comprehensive observability is justified by the savings from reduced downtime, improved compliance, and faster incident response. The key is balancing depth with efficiency, ensuring that observability delivers maximum benefit without overwhelming budgets. Human oversight remains indispensable in interpreting observability data. Automated systems can generate metrics, identify anomalies, and even propose solutions, but human judgment is needed to determine significance and context. For instance, a spike in token usage may be a harmless anomaly or a sign of misuse, depending on the situation. Human operators bring contextual awareness, organizational knowledge, and ethical reasoning that machines cannot replicate. Oversight also provides accountability, ensuring that observability does not devolve into blind automation. By combining automated monitoring with human interpretation, organizations achieve a balance of efficiency and wisdom, ensuring that observability guides actions that are both technically sound and socially responsible. AI-assisted monitoring represents the next step in observability evolution. Machine learning models can analyze vast amounts of telemetry data to detect patterns, anomalies, or emerging risks faster than humans alone. For example, AI systems can predict failures before they occur by identifying subtle shifts in latency or error rates. They can also cluster anomalies, reducing noise and highlighting the most critical issues. This collaboration between AI and human oversight creates a powerful synergy. AI accelerates detection, while humans provide context and decision-making. Together, they transform observability from a reactive tool into a proactive system capable of anticipating and preventing problems. As systems grow in complexity, AI-assisted monitoring will become essential for managing the sheer scale and intricacy of observability data. Benchmarks provide another way to measure the effectiveness of observability systems. Standardized metrics such as mean time to detection, mean time to recovery, and false alert rates allow organizations to compare performance across teams, systems, and industries. Benchmarks create accountability and provide targets for improvement. For example, if one organization can resolve incidents in minutes while another takes hours, benchmarks highlight the gap and motivate change. They also foster industry collaboration, as shared benchmarks encourage the development of best practices. By adopting benchmarks, organizations ensure that observability does not remain a vague aspiration, but becomes a measurable, improvable capability that contributes directly to reliability and trust. Future directions for observability point toward deeper integration with safety and governance layers. As AI systems become more complex and powerful, observability will not be limited to technical performance but will extend to ethical and compliance monitoring. This means tracking not only latency and errors but also fairness, transparency, and adherence to policy rules. Observability frameworks will increasingly merge with governance platforms, creating unified systems that monitor both technical health and ethical compliance. The result will be AI systems that are not only observable but also governable, aligning technical performance with societal values. This evolution ensures that observability remains relevant as AI becomes more central to critical infrastructure and decision-making. As AI expands into multimodal domains, observability must adapt. Monitoring text-based prompts and outputs is only the beginning. Future systems will need to capture telemetry across images, audio, video, and even sensor data, ensuring that behavior remains transparent across modalities. Observability will need to track how inputs and outputs from different channels interact, identifying cross-modal errors or biases. This shift underscores that observability is not static but dynamic, evolving alongside AI itself. By preparing for multimodal observability now, organizations position themselves to manage the next generation of intelligent systems responsibly. Observability thus serves not only today's needs but also tomorrow's challenges, anchoring AI adoption in transparency, accountability, and trust. Observability is therefore best understood as the nervous system of AI applications. It senses what is happening, communicates signals across components, and guides corrective action. Through traces, spans, and logs, observability provides visibility into performance, cost, safety, and compliance. By adding mechanisms for alerting, aggregation, and AI-assisted analysis, it transforms raw telemetry into actionable insight. Balancing granularity, cost, and scalability ensures that observability remains effective across enterprise deployments. Most importantly, observability provides the transparency that underpins trust. It ensures that systems are not black boxes, but visible, accountable, and governable. As organizations prepare for multimodal AI, observability will serve as the foundation for reliability, bridging the gap between technical capability and human expectation. It is not just a tool for developers, but a framework for society to understand and trust the AI systems that increasingly shape our world. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.